NanoHub.org.
Online simulation, and more for nanotechnology.
It's my pleasure to introduce Richard Couperthwaite. He's a PhD student in the Department of Materials Science and Engineering at Texas A&M. Before coming to Texas A&M, he got his undergrad degree in South Africa, also in metallurgical engineering, where he spent quite a bit of time actually developing alloys. And since coming to the US, Richard has been working on using materials informatics in the design of materials, specifically thermodynamics. And BAREFOOT, which is the framework he will introduce us to, is the culmination of this work. So thank Richard and Raimundo, his advisor, for presenting here. And without further ado, Richard, take it away.
Thank you for the introduction, Professor Strachan. So going into it, I'm going to give a short little presentation just to give a little bit of the background on the BAREFOOT framework. The question and answer session is up, so if you have questions, both Dr. Ariave and one of my colleagues, Brent, will be answering questions as well. If it's a simple answer, I'll answer through the presentation. So put your questions into the question and answer box as we go. So all of this comes to a large degree from the idea of accelerated material design. And this idea of accelerated material design is one of the aims of the integrated computational materials engineering sort of concept or framework thinking, which was then also formalized in the Materials Genome Initiative. And the idea is we want to be able to identify and develop materials faster. The standard materials development system or framework up until this time, it's taken 10 or more years to get new materials developed. And the idea is to use a combination of experimental and computational techniques combined together, integrated together to accelerate material design. And a large part of that goes back to the concept that was proposed by Greg Olson, which is the idea of materials as a system and the whole relationship in a material between the process, the structure, and the properties, and the ultimate performance of them. And in material science as a whole, we have many models and experiments that allow us to probe those relationships, the process, structure, property, performance relationships. In recent years, one of the focuses and one of the developments particularly in experimental work has been the idea of high throughput experiments. And this started in thin film testing, but with the development of more efficient additive manufacturing techniques and better additive manufacturing techniques, as well as more understanding of additive manufacturing, that has become a potential avenue for high throughput experiments of bulk materials rather than just the thin film analysis. That's all very well and good. We can model the relationship of process, structure, property, performance as it goes up, and we can see what the effect of those is. But for design, we need to effectively invert those relationships, and we need to be able to go from saying, I have a specific performance that I require. What processing and structure do I need to attain that performance? And that's not always simple to do, that inversion of this process, structure, property, performance sort of relationship. One of the more common solutions, and it's become a common solution because it's a typically robust solution, is the idea of using Bayesian optimization. And the BAREFOOT framework falls into that category. It is a Bayesian optimizer. So just very briefly, Bayesian optimization is typically a black box optimization approach. We don't need to know what model we're optimizing. We create a surrogate model for it. all we can do is we can just query and get information out of this black box. So we create a surrogate model. One of the more common techniques is to use Gaussian processes. And then we use an acquisition function. And this is demonstrated in the figure on the right. We take an evaluated point, we construct the acquisition function, and we use that to identify the next best point to query. We then query that, update our surrogate model, update the acquisition function, and then we can identify the next best query. And that process repeats itself until we either run out of resources or we've achieved the goal that we want to do. The main reasons why we use this kind of optimizer is that it reduces the cost. We could conceivably just put down a grid of samples and analyze all the samples. And this takes a lot longer. It has costs and whatnot that are added to it. Whereas if we use something like a Bayesian optimization, we're able to target where we want to use, where we want to do experiments. And so we manage to reduce the cost slightly. Generally, Bayesian optimization as well is a good global optimizer. It doesn't typically get stuck in local optima, although it can, but it generally is a global optimizer. And the other side of it is that this process is incredibly flexible. There are plenty of different surrogate models that can be used. I've mentioned Gaussian processes. There are other newer ones that are coming out that are actually even more efficient than Gaussian processes. And the acquisition functions vary greatly as well. So there's a lot of flexibility in the process. And that's why we use Bayesian optimization. In material science as a whole, one of the advantages and one of the strengths of material science is that there's often more than a single model for any given property that we're trying to evaluate. And very often those models differ in accuracy. And that's typically because way back in the 1950s or 1960s, someone proposed an empirical model that allowed them to predict a material property. As computational capabilities increased, we started getting finite element models, and those became more accurate than the empirical models that were initially developed. And we go on, and because empirical models rely on different assumptions, you get different empirical models with different assumptions. As illustrated in the figures on the right, if we want to evaluate the mechanical properties of a material, the stress-strain relationship, we can use the isostress, isostrain, or isowork models. And this is for a dual-phase material, where the isostress is a model where we assume that the stress is equal in the two phases. Isostrain, the strain is equal, and isowork is obviously then the work is equal in the two phases. Each of those has different assumptions. Each of those gives different results. But then we also have a much more accurate, which is the representative volume element model, which is a finite element model, that allows us to model those features. And so we can see that each of the colored models, the green, the red, and the blue, they capture some of the effects in some of the region of the space, but they never capture it everywhere. But all of them, as I've said, they capture the information in certain regions of the space. And so they all have information that is useful to us. And this is where the idea of multi-fidelity model fusion comes in. Is that we try and use the information contained in a variety of reduced order models that are relatively cheap to evaluate. The comparison here is the RVE takes about 4 hours to evaluate. The isostress, isostrain, and isowork all take under a second. So we can use the information in these lower order models, these empirical models, and gain information about the truth model, which is the RVE model in this case. And so the idea is that we want to then be able to optimize the properties of a material with the lowest number of evaluations of the most expensive information source, and thereby we decrease the cost again. So those are a very brief overview of the ideas and the concepts behind what we want to do in the Barefoot code. Just a few notes before we do this, and I see I've got a spelling mistake. The Barefoot code is coded with the multiprocessing options in Python. The multiprocessing doesn't work or isn't compatible with Jupyter notebooks. So I had to modify the implementation to use threading, multi-threading, rather than multiprocessing. So if you want the full code that is optimized for use on high performance computing clusters, please go to the GitHub repository and get it from there. Also, the most recent code will be there as well. So the NanoHub tool is a demonstration of the framework and what the framework does, and we'll go through the Reification fusion approach, so the multi-fidelity model approach, and then look at batch and sequential Bayesian optimization, and then give a demonstration of the Barefoot approach itself, which is a combination of the batch and the Reification approaches. And these are all implemented in the framework and available. If you open up the tool on NanoHub, this is what you should see as the opening screen. The idea with multi-fidelity fusion, so at least from this side of things, we want to start off, let me just get some of this. So for the multi-fidelity fusion, we're going to assume a ground truth, and we're going to give a very basic example. So the idea here is to use a sine function as the ground truth. Let me maybe see if I can increase the size of mine. Okay, so we're using a sine function, and as I say, this does work with noisy data as well. For simplicity, I'm not using noisy data in the example, but it works with a noisy information source as well. And by using a Taylor expansion of the sine function, we define two reduced order models. So these are relatively simple models, and we just need to implement them in Python, which is fairly straightforward using the NumPy the NumPy side. Obviously, these are just some needed imports for the notebook, so you can run those. So to get an idea of what we're looking at and what the models look like, we want to just define an input space, which is approximately from -pi to pi, and we want to evaluate all the models and plot the results. And so here we can see the three models. So we've got the ground truth model, which is the sine model. We've got two reduced order models that at various points are more accurate to the truth model than the other. So reduced order model 1 is more accurate over most of the design space, but model 2, from about a value of 2, becomes much more accurate. And so it provides more information. So to go through the Reification fusion approach is summarized into basically 3 steps. 1, we need to include model discrepancy. And model discrepancy is the difference between a particular model and the ground truth, or the truth information source that we're using. We're then going to reify the models, or the process of reification, which is a term that's used to describe the estimation of the correlation between the models, because fusion under known correlation is significantly easier than fusion under unknown correlation. So the reification process estimates the correlation, and then we do the model fusion under known correlation and get a fused model as the result. So to go back to the idea of model discrepancy, discrepancy and fidelity are the opposite sides of the coin, where model fidelity is the accuracy of the model. So how accurately does that model predict the truth value? And so in order to account for the difference between a reduced order model and the truth model, we use model discrepancy, which adjusts the variance of the model. So as you can see, in this gives a demonstration of it. So if we have truth model evaluations at the red crosses, and we have a reduced order model that we've evaluated at the blue stars, we can create a Gaussian process surrogate model, which provides a mean and a variance prediction, which is the pink line. And so we can see the mean, we can see the variance, which gets larger in spaces where we don't have a lot of information. But then we want to also be able to evaluate how accurate that model is. And so we evaluate the difference between the mean of the Gaussian process and the truth function at points where the truth function have been evaluated. And we add that uncertainty or we calculate what that difference is, and we fit a second Gaussian process to that discrepancy. And the mean of that second Gaussian process provides this adjusted variance that we add to the model. And this means that when we start fusing the models, the variance at those points is associated with how accurate that model is to the ground truth. Okay, so that's what so we want to use this total variance and run that and look at that. Okay, so for the particular example that we had up above, which is the sine functions, we can do that. So let's take 10 evaluations from each model, and for simplicity, we're just going to evaluate them all at the same point. And we'll go through from there. Okay, so now we can evaluate each of them, and let's just see where we've evaluated it. I've just done a linear sampling of the points, and we can see this. Now we have to look at, or we can look at and say, what's the discrepancy? So all we're doing is we're just taking the difference between each of the models and the ground truth at each of these points, and we can see that the discrepancy changes. Now, we've taken the absolute value of the discrepancy because standard deviation and variance needs to be positive. So it's purely related to that. And so again, we can see that on the whole, model 1, reduced order model 1, has lower discrepancy than model 2, except from about 2 onwards. So now we want to create, so from that, so now that we've got both the evaluated points and the discrepancy, we now want to create the Gaussian process models. So these first 2 sets of models are for fitting the points that we have from each of the models. And this GP model class, we use the George.py module for the Gaussian process models in the framework. And what we've got in the Barefoot framework is this GP model class that wraps the George.py module and just simplifies some of the function calls. And so I've tried to highlight here what the various inputs are that are required. But essentially, it's the same as with any other Gaussian process model, where we need the input values that we have, the output values that we're trying to fit, the characteristic length scale, because this is the squared exponential covariance function, so we have a characteristic length scale per dimension. The signal variance is the multiplier before the covariance function. The noise variance, or the nugget, is added to the covariance function to help make the inversion of the matrix a little bit more stable. And then possibly a bit of an oddity is that we have to explicitly specify the number of dimensions in the input to that. So that's fairly simple and straightforward and runs very nicely. It doesn't give any outputs at this point. And so we can now get the model mean and variance over the entire space. And so we can get that. And the idea is then we want to, so this is for our plotting so that we can see how it looks. Here we want to evaluate the discrepancy specifically. So now, as I said, we evaluate from the mean of the GP that fits the points, we evaluate the discrepancy. So we need to evaluate the mean at the points that we've tested, and then we can calculate the discrepancies or the errors as the absolute value between the truth model values at those points and the values that we have. So we've got the truth model values at those points and the values from the GPs. So we run those. And then again, as before, where we create the GPs, we now create GPs using this error 1. And to keep it consistent with what's done in the Barefoot framework, we convert it onto the standard normal, which means you subtract the mean, divide by the standard deviation. And so we want to keep that consistent with, otherwise the results later don't match up. And now we can get the discrepancy means. The process doesn't worry about the variance of these error models. All we need is the means. Okay, but as we've done the conversion to the standard normal, we need to convert back to get the actual error values rather than the values on the standard normal distribution. And so our total model error becomes the variance from the model of that information source, and then the squared value of the mean, because this mean is the standard deviation. So in order to make it a variance, we need to square it. And so we can combine that and we can plot those and see what they look like. And as noted before, for model 1, we said that was quite a lot more accurate. So you can see that the light green error, which is the total error, is much smaller than the error for model 2, where the error is quite a lot larger. But what must be noted in all of these is that, as you can see, the truth model function, which is the light dotted line, is within the error bounds of each of these models and the total error of each of these models, whereas it's not in the error bounds of the actual GP models. But because we've got it within the error bounds of the total error, the fusion process can actually match it and get the correct result. So reification, the process here, and I'm not going to go through this in great detail. You can read it if you're interested. The idea is that we reify one of the models. So reification starts by reifying one of the models, which means we assume one of the models to be true. And when we do that, we can then calculate the errors relative to that model for the other models. And we can go through the process of calculating each of those errors and get the covariance, and we can then calculate the correlation coefficients. And here we say the row 1 is the correlation when model 1 is reified. So we assume that model 1 is true. We then do that pairwise. We do it again with the second model, and we say, let's assume that model 2 is true, and we get row 2. And we then take the variance weighted average of those two correlations as our average correlation. And this is then done, if you've got more than 2 models, this is done for every pairwise combination of the models. And we calculate those correlation coefficients. Code-wise, this is the code that does that. In the framework itself, this is combined with the Fusion code, so it looks a little bit different. But the idea is that now we have the correlation coefficients and the two sets of the variances of the models in a matrix form. For model fusion, what we're trying to obtain is this kind of model where we have a prefactor for each of the means of the different models that we have. And the idea is that we want to solve for these values, which can vary over the design space as well. We want to minimize this or solve this minimization problem. Now, we use the solution that's been proposed by Winkler, and we end up with a mean and a variance, a fused mean and variance. And here we see that we've got these average correlation coefficients that sit in here. And that's what we end up using. And these sigma values here are the total variance of the models, not just the GP variance. So a lot of nice math gets written down and condensed down into a couple of lines of code. And we can create that. And the output here is the fused mean and the fused variance. And you'll see that we use the correlation coefficients we calculated previously and these two matrices that are required to get the variances. Okay. And now we can plot that. And here, it gets a little bit difficult to see because the fused model matches the reduced order model 1 really, really well for most of the space. But we can see that the variance of this model fits quite nicely to the truth model, and it matches nicely. So one of the challenges, and this is a dual challenge, when you've got a very low dimensional space like we have here, you can get these discontinuities where it kind of collapses down to zeros. And we don't necessarily want that. We want a slightly smoother, a smoother variance on the model. But on the other side, if we go to a very high dimensional design space, we're going to only be able to evaluate a very limited amount of points for the fused mean and variance. So in order to combat that, we create a Gaussian process model of the fused mean and variance. And because of the nature of this one, we take a subselection of these models. And this is a holdover from the work that was originally done on the reification. And it's not entirely necessary to do when you start sampling large spaces, but it does sometimes help if you've got areas where you might have pockets of close evaluations of the fused mean and variance. So we construct a GP again, and we can then evaluate that to plot it. And now we have a much nicer or a much smoother evaluation of the process. But still, we haven't really changed anything about it other than reducing the variance slightly. So it's nice to be able to do that, but obviously we aren't always interested in finding the exact fit to a model, and it's not always feasible to find that. But we want to know that we've gotten closer to where the maximum is, and we've got a better predictor of where the maximum is than we did previously. And so if we evaluate all the models that we have, we've got the truth model, we've got model 1, model 2, and we've got this fused model. And if we evaluate them over a very fine grid, so 10,000 points, because under the assumption that we've got a black box function, we don't know where the maximum is, we can actually find it explicitly in this case. And we run that and we say, right, where is the maximum? And so we say the true maximum is at 1, or as close to it as we can get. Is the maximum value is 1, and the location is at 1.57. Each of these models gets quite far off. The reduced order models are relatively far off, but our fused model, we've managed to get closer. So the fused model is a better predictor of the maximum point than either of these two models, and that's what we're looking for. So that's the basic idea behind it. But obviously we don't want to have to go through specifying all of those values and specifying all of that process every time. So the framework has it built in as a specific, as a Python class. Now, before we can sort of go into it, the Python class allows you to use a dictionary of inputs that provide your model characteristic length scales, noise variance, signal variance, and things like that. And this is the dictionary structure that's required for that, for the reification class. And so we can see that we create that class and we put in all that information, and we have the reduced order model testing points, the reduced order model evaluation points, the truth model test and evaluation points, and then all the different hyperparameters that we require for those models. We give the number of reduced order models, the dimension, and then obviously the covariance function that we want to use. That makes it a lot easier to call that in the code. And we can then go through that whole process that we've done up here of defining the discrepancies, doing the reification, and building the fused model. That all now gets reduced down to a single command, which is this create fused GP. And that creates that model within our reification object. And then again, we just say predict fused GP, and we can get our fused mean and fused variance. Okay. The difference here is that when this whole program or the framework was set up, the initial acquisition function we used was the knowledge gradient acquisition function. And the knowledge gradient requires a covariance matrix. So this variance that comes out here is the covariance matrix, not the diagonal. But we can quite easily get that. NumPy has a built-in function that allows you to extract the diagonal from a matrix. So that gives us our variance. And if we plot that again, we can see that the result is the same. So from what we did previously to now having essentially 3 or 4 lines of code, we've managed to achieve the same result. So that is what the framework is designed to do, is try and make this a lot easier. But obviously, just having the reification fusion, we can create a fused model. How do we use that as part of an optimization approach? And the idea is that we integrate that with a conventional Bayesian optimization approach, where we use the fused model as the black box source for the Bayesian optimization. And so, as an example, we look at this mechanical model problem that I initially showed in the presentation at the beginning, and we look at these 3 models and the finite element, the RVE model. Now, in order to do this problem, we had to use thermocalc to get our ferrite and martensite compositions. But because I can't load thermocalc in the NanoHub system and run it there, we created a model, a GP model of that of the thermocalc outputs. And so we need to load that as as the first thing, so that we've got that available to query and get our information out. So the next, obviously we need to define the functions. In this case, the functions were originally defined on 4 dimensions, but for simplicity and to make the code run a little faster, I've fixed 2 of the dimensions at good values. These were chosen essentially because we could find a nice maximum at those points. So we just need to define those. We've loaded the thermocalc model. The RVE model is loaded as a Gaussian process as well. Again, means that we can actually run the example. So for the calculations, we need to define initial values, and the commented code here is the code that was used to define the initial values that are in this pickle file that we're going to load. But so this shows you how you would do it and construct it, and the framework accepts the initial data in a dictionary of this format, which is shown here. So if you want to use specific initial values, you can load them. And for a lot of the testing that I've been doing of the framework, I've had to specify these dictionaries so that I can use the same initial values for multiple calculations. If you don't need to worry about that, the framework allows you to calculate the initial values anyway, without a problem. So as before, we need to define our Gaussian process hyperparameters, and this goes into this model parameter dictionary. And we then create our, so this is not explicitly needed when you're doing only the model reification. So let me make a note of that. It's not explicitly needed here, but it is explicitly needed in the Barefoot framework itself, which is why I'm using it. So just keep that in mind. So we create the model reification object, and the next step is that we want to define the fused model hyperparameters. So we want to create, because when we create the fused model, we need those parameters. So we create those, and we also, in this particular example, we're going to use expected improvement as the acquisition function, which means that we need to have the current maximum that's available. So we take that from the initial dictionary, we get the maximum value, and this psi parameter, which is the weighting in the expected improvement between exploitation and exploration, we take it as the default value, which is 0.01. So then we just need, this is just creating some lists so that we can actually do the plotting later. So the next step is a long block of code that can't be broken up because it involves a loop. So I'm going to explain what that loop is doing, and then we'll run it. So the idea with the reification approach is that we only evaluate the truth model after a certain number of iterations. During all other iterations, we need to define which reduced order model we're going to query and which point we're going to query. So the idea is we start by evaluating all the test points, or we evaluate the test points from one of the reduced order model GPs. We then take each of those test points, temporarily update the fused GP using that model, that value from the GP model, and then evaluate the acquisition function and record the maximum. And we then go through that for every combination of test point and reduced order model. And at the end of that, we have a batch of points that have an index of test point and model and an acquisition function value. And we say which one of those is the largest acquisition function value, and then we evaluate that test point from the chosen model. We then repeat that until the iteration limit has been reached for evaluating the truth model. And at that point, we create the fused model, put a fine grid over the entire space and sample the fused GP model, and we choose the input that corresponds to the maximum of that fused model. So this is a greedy approach. It doesn't use an acquisition function, but we can use an acquisition function if necessary. And so we then evaluate that point from the truth model and update the reification object. And then we repeat that again and again until our total iteration limit is reached. So that starts the loop. Now this does put out an interactive plot, so it should start showing there. As I note here at the bottom, this process is a stochastic process. It relies on random number generators. So two runs with the exact same starting point are likely to produce different results. And part of this is going to take a little while to get started. So while we can look at this, we say, separately to this, and then we're starting to get it coming out. So the plots here that we've got here show the evaluations of the RVE model and the strength parameter, the normalized strain hardening rate that we're using as our target objective, but also show the total number of iterations that we're running and the number of model evaluations for each of the reduced order models. And you'll see this updates because the limit is at 5 when it updates, when it actually does an RVE evaluation. So you can see that these update, and it's slowly choosing. At the moment, it seems to be that it's using mostly the isostrain model. And so that carries on and works through. While that goes, and we can leave it to generate a bit more data and go back to this. I took 30 sets of initial data or 30 calculations with the same initial data point. So this is a demonstration of where the stochastic process comes in. These all started with exactly the same initial point. And we go through and I ran that to see what the results were. And you can see that by about sort of 30 iterations, it's essentially plateaued off. But it's still optimizing, and you can see here we can actually see the effect. We've gone through the 5 iterations. We've now got it. We've gone from a value of around 8 up to 26 as the normalized strain hardening rate. So it is optimizing quite nicely. And it carries on performing in the same way. So that's a summary of the reification process and how we'd apply that as an optimization in its own right. Are there any questions on that? Yes. Okay. So just going from the bottom, the kernel hyperparameters are specified explicitly. They aren't fit. It reduces the time required by in order to do the optimization. If you put the hyperparameter optimization into it, each iteration starts taking significantly longer. So that's one there. And then there was the problems with the barefoot module, which we'll get to. And I did test it and try and make it run. So I'm a little bit confused as to what's happening. Okay, so we'll leave this and we'll go on to the Bayesian optimization. Okay, so the idea behind Bayesian optimization, and if we just set it up so that it actually runs everything quickly, the idea here is that Bayesian optimization, as I said, we want to be able to optimize a function, a black box function. So if we take this is a fairly common standard test function, the egg holder test function, which is defined here. And so the same process is we need to define the process. We need to define a Gaussian process model over an initial sampling. And then we use expected improvement again. This is the full definition of it. And we use that acquisition function. You can see that in the Python code. And it's just taking a little bit of time. So the idea is that once we get to Bayesian optimization, the steps that we follow is to evaluate the surrogate model as extensively as possible, as computational limits apply. And then we calculate the acquisition function for each of those points. And we can determine which point has the maximum value, and that's the next point that we evaluate to be true. And we then add that information to the surrogate model, and we continue optimizing. So this is what that kind of optimization looks like in real time. And the difference is that we look at the batch, and I'll come back to that because it's working a bit better. So that was the initial optimization, the initial, and here we're using the gap metric, which is a way of defining the data. But as was pointed out, we typically train the hyperparameters because we don't know what those kernel hyperparameters are. So the batch optimization approach that we use is it takes that assumption or that knowledge that we don't know what those hyperparameters are, and we then sample from the hyperparameter space. And this figure gives a demonstration of how your GP model can vary depending on what your hyperparameters are. And then also looking at your acquisition function. Depending on what your hyperparameters are, your acquisition function can be different as well. So if we take a large sampling of potential hyperparameters, evaluate the model and the acquisition function for each one of those sets of hyperparameters, we then get a large sampling of the space and potential hyperparameters and potential next best points. And we can then cluster those points to identify the batch size that we need. So we create clusters that match the number of batches that we need. And so that process, it then follows exactly the same process on the of the sequential Bayesian optimization, whereby, but instead of evaluating a single point at each iteration, we now evaluate a batch of points. So we make an assumption that we can evaluate our function in parallel, and this is where the high throughput experimental approaches come in. So again, we apply this batch optimization to this mechanical model problem. And again, it's stochastic, so we can see that there's a difference in performance. But we can see that it does actually, it works even slightly better than the reification fusion approach in the end. On the average performance, they are fairly similar, but the batch Bayesian optimization is slightly lower variance. So, but this is on the truth model evaluations, and I need to note that if you assume that there's a certain amount of time taken for each evaluation, the batch approach under the assumption that each evaluation of the truth model happens in parallel, and each set of parallel calculations takes exactly the same time as a single calculation, the time taken to reach that point is significantly shorter than the time to do it sequentially. And that's where the real benefit of the batch approach kicks in. So please go through that in more detail to see what's happening there. And let's then go through and look at what the Barefoot framework is as a whole. So as I said, the Barefoot framework combines these two. This is where's that one? Okay. So the Barefoot framework, as I said, combines the batch and the reification approaches. So in this overview of the framework, the green section is the formulation of the reduced order surrogate models and the discrepancy models. The blue section is for the evaluation of which points to query from the reduced order models. Okay, and here from the reification approach, we have the number of models and the test points that are important or imported from the reification approach. We then evaluate each of those points on each of the hyperparameter sets that we define from the batch approach. And so we end up with it does take a little bit longer, but we get the total process, and the hyperparameter sets are defined for the fused model only. We still need to define hyperparameters for these surrogate models. And so this creates a loop that we evaluate each model, each test point, each hyperparameter set, and we get a maximum acquisition function. And then we can cluster those values, and we don't cluster them only on the acquisition function values. Found it kind of clumps the results a little bit. It still keeps them too clumped together. So the clustering here is done on the model index, test index, and acquisition function value. So it does. It's a three-dimensional clustering that seems to work a little bit better. Then we follow a similar process when we want to evaluate the ground truth model, but in this case, we don't have the iterations over the models and the test points because we're not evaluating those. We're only evaluating the ground truth. So we keep it on just varying the hyperparameter sets for the fused model, and we evaluate the acquisition function, and we then cluster those results. So this is more your typical, your standard batch approach, and we evaluate the ground truth. And so that's a very brief overview of the approach. The idea is that we've set it up so that it's very simple to set up the function or the framework as a whole. And it requires just it requires an initial call to the framework object, and then we can initialize the parameters. And mine is actually working. And the optimization, this run optimization, starts the calculation running and with all the parameters that we've set. So this, what you can see, is the output in a log file so that you can keep track of how the calculations are going. And we get those evaluations out. There should probably be some kind of result coming out here. But as a comparison, we can see that when we took those initial 30 parameters and we ran it, the end result is still the same, but the Barefoot framework, by using that reification approach, is actually helping and getting sort of matching the reification steps a little bit better than the batch was. And it's keeping the variance lower earlier as well. So that gives a very broad overview of it. But here's the results from the calculation. As you can see, it's taking a little while, but you're starting to see the evaluations of the different reduced order models. And this is a comparison.
Richard, if I may interrupt you, I mean, since
Yes.
we're running out of time, can you just go to the last slide, because the last
Yes.
picture of the results?
Yeah.
And I just want to, no, in the notebook itself. Can you go down? DR1, when you compare with time. So,
Yes.
in a nutshell, this is probably the most interesting plot. This just tells you how much you would save in time relative to a Bayesian optimal experimental sequence by using the batch approach.
Right.
So, that makes a big difference. Even when you're doing Bayesian optimization, that makes a huge difference when you're trying to apply this to expensive problems such as material discovery.
Yeah, this is great, and I think you have the publications linked.
Yes. Most of the publications are linked. So is that the GitHub is linked there as well. My emails are available on the GitHub. So if there are any questions or you want to look into this further, I am more than happy to assist on any of that.
With that, I'd like to thank Richard and Raimundo for a great presentation, lots of material, and I'm sure all of us will spend time going back through the notebooks and reading the papers. But this was a great introduction to your work, guys. So thank you very much.